All right. So our next lesson is going to be on rotation 2. In this lesson, we're going to look at moments of inertia and we're going to look at torque. In this lesson, we first look at moments of inertia. Just as we found that the linear components of distance, velocity, and acceleration also had angular analogs. Instead of talking about acceleration, we could talk about angular acceleration instead of velocity, angular velocity. Likewise, mass has an angular analog as well. One way we can think about mass is that mass is basically an object's resistance to acceleration. If you have a very light object, one that has a very low mass, it takes a very, very small force to result in an acceleration. If the object had a larger mass, then applying that same force would result in a much, much smaller acceleration. And that's sort of, you think about just our general Newton's second law equation, that the net force is mass times acceleration. That's sort of what it says, is that, with the same force, is that increasing the mass is going to decrease the acceleration. That mass is sort of a resistance to being accelerated. Now, in the same way that, an acceleration is a linear thing. It's a sort of a change in the rate in the linear direction. But in the same way we're talking about angular, talking about rotation, is objects that have a resistance, or objects also have a resistance to angular acceleration, to being sped up in their rotation rate or slowed down in their rotation rate. If you have a very large branch that's in your hand and you try to turn with it, it sort of resists that turning somewhat, whereas a smaller object doesn't resist that turning as much. And so we call this resistance to angular acceleration the moment of inertia. Okay, and so the moment of inertia is sort of the analog to mass in terms of rotation. So it's basically an object's resistance to having its rotation rate changed. So an object with a large moment of inertia requires more effort to change its rotation rate than an object with a small moment of inertia. So an object with a small moment of inertia would be very easy to get it to speed up or slow down in its rotation rate, but an object with a large moment of inertia would be much more difficult. So let's take a look a little bit at what this is exactly, how to figure it out. So the moment of inertia of an object depends on two factors: the mass of the object and the distribution of mass with relation to the axis of rotation. So the mass should be pretty straightforward here. If you think about it, very light objects are very easy to twist. They're very easy to get started to turn, or very easy to slow down if they're already turning. Heavy objects, ones that are more massive, take a lot more work to slow down. If you have a very, very heavy object that's spinning, even if it's spinning slowly, you may have to really push hard on that to get it to stop. And so that's the first piece, is the mass. The second one is the distribution of mass, and that's our second bullet point here. The farther the mass of an object is from the axis of rotation, the greater the moment of inertia. Okay, and so if the mass is farther away from that axis, you'd have a greater moment of inertia. If the mass is very close into the axis, then you have a small moment of inertia. And so, if you were thinking about it a little bit like this, if we had, say, a barbell with the masses out here, and we're rotating it about, this axis right here, is that this barbell right here would be harder to get rotating than a barbell where we took the same two masses and put them close together. The top one would be much, much easier to rotate than the bottom one was, or at least to get started rotating or to stop rotating. The bottom one is going to have a higher moment of inertia, even though the two objects have the same mass, because in the bottom one, the masses are farther away from the axis of rotation. So another example would be if you look at the bottom down here, we have two cylinders. We have this one that's on the right, that's a solid cylinder. This one that's on the left, which is a hollow cylinder, has a hole cut out of it. Let's suppose that we're going to rotate both of these about sort of this axis right here. And so about that center axis where sort of at the center of the circle, if we basically drew a line down the middle of the cylinder there. Let's assume that these two objects have the same mass and the same radius. Okay? And so they weigh the same amount, they have the same mass, they have the same size overall here, no differences, other than the fact that in the right-hand cylinder, the mass is spread out over the whole cylinder. In the left-hand cylinder, the mass is all going to be some greater distance, or not all of it's greater distance, but most of the mass on average is a greater distance away from the axis of rotation. Because of the fact that on the hollow cylinder, the mass is farther away from the axis of rotation, the cylinder that's on the left, the hollow one, would have a greater moment of inertia than the one that's on the right. It would actually be harder to rotate that one that's on the left than the one on the right. It's harder to rotate the hollow one. You can actually test this out if you have two objects that weigh the same, have the same radius, and one's hollow and one's not. Put them on an inclined plane, let them roll, And what you'll find is that the object that is solid will actually end up rolling seemingly faster. It will roll faster down the incline. It will reach the bottom of the incline before the one that is hollow, if they have the same mass and the same radius. And the reason why is because it's harder to get the hollow one to spin, to start rotating, because of the fact it has a higher moment of inertia. Another place that this actually shows up is sort of something that's intuitive to most people. Normally when you walk with your arms down by your side. But if you have to walk across like a thin beam, like let's say that you have there's like a gap here, and then someone's got a beam plank that you have to walk across, is that you have a natural tendency, if it's really, really thin, to raise your arms up. And so, if you normally walk with your arms along your side, if you have to walk along a plank, you have a tendency to lift your arms out like that. You stretch them out to try to keep your balance. Well, the reason why is because whenever you stretch your arms out, you are making your mass, at least part of your mass, your arms get farther away from your body, farther away from your axis of rotation, and you increase your moment of inertia. With an increased moment of inertia, you are less likely to rotate, and that is less likely to fall over and fall off of the plank. And so this is also one of the reasons why, if you look at tightrope walkers, tightrope walkers, whenever they have those very, very long sticks that go out here, the long piece right here. And so one of the things that does is that that makes their moment of inertia much, much larger. It's much harder for them to rotate, and thus less likely to fall off the tightrope as they're walking across that. Greater moment of inertia means less likely to want to rotate. It's harder to rotate, and so that's sort of what that is. So that's moment of inertia. So if we want to calculate it, so let's say we have this. For a set of n point masses, and so when we say a point mass, we're saying an object that either all the masses at a single point, or one where we can approximate all the mass at a single point. Okay. Each of the masses of the n point masses, which we call mi, and so I is however many masses we have, in kilograms, that are located some distance ri, and so in meters from the axis of rotation, the moment of inertia, which is given by I, of the set of masses is given by this summation equation here. The moment of inertia is equal to sum over all the masses from our first mass up to our last mass of the mass of each object times its rotation squared, times its radius squared. So let's suppose that if we have, we talked about that barbell before. And so, if we can treat these two masses as point masses, then, and we're rotating about, say, this axis right here, then the first m in this summation would be, we'll say that's m1 right here. We'll say this one's m2, is that the radius, this would be r1, this would be r2. And so if we were setting up the summation equation, we'd say, okay, well, the total momentum of that is going to be equal to mi ri squared. So the first mass is mi, and then m1 r1 squared. Our second mass, since we're summing them, we'll just add that up, would be m2 r2 squared. If we, for some reason, decide to add a third mass that was out here, we'll call that m3. Its radius is going to go all the way back to the axis, and so that would be our r3, and so we'd say plus m3 r3 squared, and so on and so forth. However many point masses you have, you can just basically take the mass times the distance from the rotation axis squared and sum all those up, and that'll give you the moment of inertia. And so capitalized moment of inertia, as we said, its units are kilogram times meter squared, which makes sense because mass is in kilograms and radius is in meters and it's squared. So that's overall sort of how this would work for calculating moment of inertia for point masses. For a single point mass, then this just turns down into I is just 1, R is just 1. It just ends up being I is equal to mr squared, where m is the mass and r is the distance away from the axis of rotation. Now note that if you change the axis of rotation, it changes the value of r. In this picture that's up top is that, we said the axis of rotation is right there, but if we were to move the axis of rotation right here, then now R3 is going to be that distance. I'll switch colors so it makes it a little more clear. So R3 would be that distance right here. R2 would be this distance right here. R1 would be that distance right there. And so, just have to modify that as your axis of rotation changes. So, let's try some of these out. So suppose that we have a 10 kilogram object which is mounted on a 2 meter long massless bar. So we basically have, a bar that's right here. That bar is massless. We don't have to worry about the mass of that bar as we rotate it. We have a 10 kilogram object, which is, right here. And this object right here, for the purposes of this, we're going to treat it like a point mass. Technically, it does have some volume to it, and so it isn't a point mass. But for objects that are spherical, we can oftentimes do that if they're being rotated about a place that's farther away from the object is far away from the axis of rotation, which is true here. So in this case, what we're doing is we mount it on the bar. We're going to rotate it about the far end, and so basically we're going to rotate it about this axis right here, and so so I guess it's like going down into the plane here. But so we'll rotate it around that point right there, and so that's how we're going to rotate this object. So, question is, what's the moment of inertia? Well, in this case, we know moment of inertia is going to be equal to moment of inertia is going to be the sum of all our objects. Well, in this case right here there's only one object, right? And so really we don't have to worry about the summation because there's just one of them, right? And so with just one object here, we just say it's mass times its radius from the axis squared. All right, well, the mass of the object is 10 kilograms. Okay, and we said this was a point mass, so we can use this equation. And then the radius on this, well, the radius we're being rotated from the axis is 2 meters, it says. So then we'd say 2 meters squared. And so then that means the moment of inertia for this would just be 10 times 2 squared, 10 times 4 would be 40 units, as we said, is kilogram meters squared. And so that would be our moment of inertia of this object. All right, so that would be what it would be if it's rotated at the far end. But let's suppose that we take the same object, but this time we rotate it not around the far end, the one that doesn't have the ball on it, but we rotate it about this point right here. And so now we're rotating this rod around like that. Now, once again, is that we're going to treat this for the purposes of doing this right here as a point mass. This is actually probably, of the 3 examples I'm giving you here, we're on number 2 of this, the one that you actually probably would not want to treat this as a point mass. But let's assume that just for the purposes of this, that the radius of the sphere is really, really small. And so, if that radius is, 0.0000001 meters or something like that, so that we really don't have to worry about the actual volume of the spheres we're doing here. We're going to treat it like a point mass. So, same situation, this time instead of rotating about the right end, we're going to rotate about the left end, basically the center of the ball that's right there. So same kilogram object mounted on the 2 meter long massless bar, same situation, but what's the moment of inertia? The bar is rotated about the near end. Well, one object still. We said we're treating this like a point mass, and so that means with just one object, it's just going to be mr squared again for the moment of inertia. The moment of inertia, the mass is 10 kilograms. Well, what's the radius? Well, the object is located right here, and the axis of rotation is also located, right there, which means that the radius is 0. So then we don't have any distance from the axis of rotation, so it's just 0, which means the moment of inertia here would be 0. This is, if you think about it, sort of makes sense. If you have an object and that object is really, really small, like a marble or something, is that, very, very small objects where it's not a very large radius with them are really, really easy to rotate. And technically, if you were able to get the radius of that object down to 0, where it had no mass whatsoever, or not no mass, but had no radius whatsoever, it would take no force to rotate it. In the same way, if you had an object that had no mass whatsoever, it would take no force to accelerate it, which is a little, unrealistic. All objects do have some mass, and all objects do have some radius, even if it's very, very small. And so they would maybe have a little bit of moment of inertia, but in a technical sense, if this object had no radius whatsoever, it was a point mass, and we rotated it about its axis, it wouldn't take any force whatsoever, any effort whatsoever to make it start rotating. And you can sort of think of this once again. If you basically create a situation like this, and you took an actual physical object and put it on the end of a stick like this, when you try to rotate it about this axis, it's much harder to rotate than when you try to rotate it about that axis right there. And so, try it out sometime. You'll see that it is a whole lot easier to rotate when the mass is closer to the axis of rotation than not. So let's take an in-between on these, and let's say that same situation, but this time what we're going to do is we're going to rotate it about the middle of the bar. right here. We're going to rotate about that axis as it goes around here. And so once again, one object, we're treating it as a point mass. Moment of inertia is, since there's a single object, is just mr squared. The mass here is 10 kilograms. The radius here, in this case, well, we're going from halfway to the object, so it's just going to be 1 meter for this. So it's going to be 1 meter squared. And so that gives us a moment of inertia here of just 10 kilogram meters squared for a moment of inertia. So you can see, you know, in the first situation that we had here, we had 40 kilogram meters per kilometer squared for the moment of inertia because we're rotating the ball from a far distance away from the axis. When we put the ball right on the axis, we got 0. When the axis is in the middle, we end up with 10, somewhere in between those two values, which would be consistent with sort of what we said. So we've only had one object here. What if we had more than one object? So for the dumbbell below, what's the moment of inertia if rotated around the yellow sphere, then the blue sphere? And then what about a 0.5 from the left end? So 3 problems here. So first thing, let's rotate it around the yellow sphere. Once again, is that for the purposes of doing this, we're going to assume both of these spheres have an infinitesimally small radius, so we can treat them like point masses. So for this right here, we do have 2 masses, so let's talk about the rotating with the yellow sphere first. And so because of that, we have to sum up the 2 values here. And so what we'll do is we'll do the mass of the blue one times the radius of the blue one squared plus the other one, which is the moment of inertia for the other object, which is the mass of yellow times the radius of yellow squared right there. And so this should give me our moment of inertia because we're summing up the 2 individual moments of inertia. And so continuing on this, we would say, all right, so let's look at the blue one right here. So how far away is the blue one from the axis of rotation? Well, in the first case, we're rotating about the yellow sphere. So the blue one is 2 meters away from that. So we would say that the blue one has a mass of 5 kilograms. That's in the right unit, so we can leave it there. 2 is your radius away from the rotation, just 2 squared, plus the mass of the yellow cylinder, or the yellow sphere, or yellow point mass, which is 3 kilograms times its radius, which is 0, because we're rotating it about that yellow mass. And so that means that our moment of inertia in this first case, around the yellow sphere, when we rotate about the yellow sphere, would just, this curve cancels off. 2 squared is 4 times 5 is 20 kilogram meters per second, or sorry, kilogram meters squared. And so that would be our first value around the yellow sphere. Okay, now it says about the blue sphere. Well, in the case of the blue sphere, we're going to do the same thing. Just now, our axis of rotation is somewhere different. So in the same way, we'd still have this set up. The only difference is now our radiuses are different. So the mass of the blue sphere, which is 5 right there, times the radius. Well, for the blue sphere, if we're rotating it about the blue sphere, then its radius is going to be 0 from the axis of rotation, because it's on the axis of rotation. Then, whoops, not equals, should be plus, because we're summing up these 2. The mass of the yellow sphere, which is 3 kilograms, times the radius of the yellow sphere, which in this case is 2, because we're rotating it about the axis that's now 2 meters away from the yellow sphere. So we have that right there. So then we can sum this up. 5 times 0 squared is just 0. 3 times 2 squared. 2 squared is 4 times 3. So moment of inertia is equal to 12 kilogram meters squared. That's kilogram meters squared right there. So that would be our second situation. All right, so let's look at our third situation. I'm going to go ahead and erase what we have here. Third situation is we want to rotate this barbell about a point that is 0.5 meters from the left end. And so now, let's see, get this finished up. Point that's 0.5 meters from the left end. And so, 0.5 meters from the left end is going to be somewhere in the neighborhood, so halfway is about right here. And so we're rotating about this axis right here. Now, because of that, it means that we're going to have a radius for the blue sphere from here to here, which we said is going to be 0.5 meters. For the yellow sphere, our radius is going to be the other distance across here. Since the total is 2 and that's 0.5, this would be 1.5 meters. And so these are the 2 values that we'll use in our equation. And so let's set this up again. Moment of inertia, since there are 2 point masses here, it's going to be the sum of the 2. So the mass of the first object, the blue one, which is going to be 5 kilograms, times its radius from the axis of rotation, which is 0.5 meters squared, plus the yellow object, which is 3 kilograms, times the radius here, which is 1.5 squared. And so now neither one of them cancel out. We can just go ahead and set this up here. So 0.5 squared is 0.25. Let's see, and see, 0.25 times 5 is 1.25, I believe. And then the other one is 1.5 squared. Let's put this calculator. Let's see. So I had those up. If I'm doing this right, I'm getting 8, if my math is correct. So 8 kilogram meters squared, because, let's see, so 3 times 1.5 squared is 2.25. Actually, it's not 8. That isn't right. I should try doing my math better here. All right, so let's try this again. So first object is 5 times 0.5 squared, which is 1.25. So 1.25 plus 3 times 1.5 squared, which is 6.75. Oh yeah, I was right. I just wasn't doing my math correctly. So 6.75 plus 1.25 is 8. And so the moment of inertia rotating about this axis right here would be 8 kilogram meters squared. And that is how you calculate moments of inertia for point masses. But what if it's not a point mass? Well, you can use some various calculus techniques to figure out what the moment of inertia around solid objects are, objects that are not point masses. There are also some ways to do it using matrices and tensors if you have arbitrary axes of rotation. For the most part, is that what we'll use here is if you have an object that's a solid object, not a point mass, you just have to look up what the equation is for axis about that rotation around that axis for different objects here. So like for example, we have right here a solid cylinder or disk where it's being rotated about its symmetric axis. In that case, the moment of inertia of the object is I is equal to 1/2 mr squared, where m is the mass of our object, and then r is the radius of the object right there. Similarly, if we had a hoop, then where we're rotating it about the symmetric axis, it's mr squared. If it's a solid sphere, it's 2/5 mr squared. If it's a rod rotated about center, it's 1/12 ml squared, where L is the length of the rod that's being rotated. In this case, m is still the mass here. If you had a solid cylinder that's rotated about its central diameter, not about the symmetric axis like this one was, then it's a little more complex, 1/4 mr squared plus 1/12 ml squared, where r is the radius that's right there, and L is the length of the cylinder as it goes around here. And then you can see the rest of them here. A thin spherical shell, 2/3 mr squared. A rod rotated about its end, 1/3 ml squared. And so it works similarly here. You just have to look these up, or most of the cases when we do problems, I'll give you these values. But until you learn if you take a college physics class later on, until you learn how to solve for these, you're basically just going to look them up for the particular object that's there. So let's take a look at the next topic here, which is torque. So with linear motion, an object will accelerate in the direction of an applied force. Okay. Now with angular motion, an object will experience an angular acceleration whenever you apply a torque. Okay? And so in the same way that a force results in a linear acceleration, a torque results in an angular acceleration. Or at least an unbalanced force results in a linear acceleration, and an unbalanced torque results in an angular acceleration. So torque can be described as the angular analog of force, and is thought of as an applied twist to an object. So, if you have a doorknob, and you want to turn the doorknob, you grab the doorknob and you apply a twist to it. It's like a force. In fact, in some sense, you are applying a force to the outside, but you're applying a force to make something turn, or start turning, or stop turning. Like if you had like fan blades, and the fan blades are spinning, you want to stop them. And I guess it probably wouldn't be smart to reach in, but they're going really slow. You could reach in and grab them to stop them here. Similarly, if you have, you need to use a lever. And so, you have a big rock that's on the ground, you want to lift it, and so you basically take a fulcrum and put a lever underneath the rock, and as you pull this lever down, it's going to rotate that lever, hopefully moving the rock, and so that would be applying a twist, and so that's applying a torque. Or if you have a screw that you're trying to, put into an object or take out a screw like that, you have to apply a twisting force or a torque to that screw to get it to start rotating, or to get it to stop rotating, I guess, in some cases. So the magnitude of the torque depends on really three things. It depends on, one, the magnitude of the applied force. And so anytime you have a torque, as we said, you have to have some force that's involved. And so the bigger the force, then the bigger the torque. The second one is the distance between the application of the force and the rotation axis, or pivot. And so, in this case right here, this distance that between the rotation axis and pivot would give you one torque. But if we had, a one of these that was longer like this, and we put the force down there, is that you'd be able to create a greater torque even though you applied the same force. And so that's another one that's here. And the other one is the angle between the applied force and the radial line. And so the angle that's basically between this applied force and the radius that goes along, that goes back to the point of rotation right here. And so let's look at that in a little more detail. But those are the things that apply to torque. So torque is given by tau is equal to F times R times sine theta. And so let's talk about this. Tau is the torque. And so it's the Greek letter T, it's a lowercase, which is torque. Its units are Newton meters. F, as we said, is the applied force, which is going to be in newtons. R is the distance between the applied force and the axis of rotation, and theta is the angle between the two. And the example I'm going to give is this wrench that we have over on the right side. And so let's suppose that you want to twist this hex nut that's right here. And so in order to do that, you apply a force to the far end of the wrench. And so the things that apply here is obviously the amount of torque, the twisting power that you have, or the twisting force, the torque that you put on the hex wrench, the hex nut, is based on one, how much force you apply. A greater force will result in a greater torque. The second is the radius. This should be, once again, a little bit of common sense. If you want to be able to twist something, it's stuck, you want to grab the wrench on the far end, right? With a large value of R, you know, you wouldn't want to grab the wrench right here, and you wouldn't want to push right there. You would get a much less effective twist, right? It's not very good at being able to loosen a stuck nut if you basically try to grab the wrench near the point of rotation. You want to grab it as far away as possible. And if you want to basically have something that's really stuck, you get a really long wrench where you can apply the force a very far distance away from the point of rotation. That results in a greater torque. And so you can result in the object changing its angular velocity, speeding up and starting to rotate more easily than if you grab close. This also, think about, it's the reason why when we try to open doors, which side is the doorknob on a door? It's on the side that's far away from the hinges. You know, you don't put a doorknob next to the hinges. If you did, it would require a much larger force to result in the same torque needed to open the door. By moving the doorknob far away from the hinges, it takes less force to create the same torque, because, you know, if R goes up, then F can go down to get the same value of tau right here. Okay. Last one that's here is the angle. And so the angle is basically the angle, as you can sort of see here, between the applied force and the radial direction right here. Is that normally whenever you grab something, if you're trying to twist this, you're going to basically make your force perpendicular to that. And the reason why is because that's our sine of theta here. When theta is 90, with the sine of 90 is just 1, we maximize our torque. The closer, the smaller the angle is between those two, the less torque you'll get. To the point of, you know, once again, let's apply common sense. If you had a wrench like this and you pulled on it, you applied a force this way, would the nut turn? No. You'd be going no torque. Same thing as if you were to push directly straight down the radius. You know, it wouldn't turn. Because in those cases, is that our angle theta is going to basically be 0, and sine of 0 is 0, and we get no torque at all. And so, you know, maximum torque is going to be whenever the applied force is exactly perpendicular to the radius from the point of application back to the center of the axis of rotation. Minimum torque would be basically whenever they are parallel, the force and the radius that's there. So, or anti-parallel if it's pointing along the opposite way. So let's take a look at a way to figure out angular acceleration if we know the torque. So the relationship between them is that tau is equal to I alpha, where tau is the torque, as we've been discussing here. I is your moment of inertia that we just finished discussing, and alpha is your angular acceleration. Hey, look at this. F equals ma. Tau, which is torque, like force, is linear. M is mass, the angular sort of version, the resistance to rotation. Changing rotation is the moment of inertia. I, instead of a linear acceleration, we have angular acceleration. Once again, they're very, very similar here in terms of the parallels. So tau is the torque in Newton meters, I is the moment of inertia, and alpha is the angular acceleration. So let's try to apply some of this here. So let's say we have a question. What minimum force is required to apply an angular acceleration of 2 radians per second squared to a solid sphere of mass 200 kilograms and radius 80 centimeters? And so once again is that this solid sphere is not a point mass, and so we have to have an equation for it. And for a solid sphere, the moment of inertia, I is equal to 2/5 mr squared. M is the mass of the sphere, and 80 is the radius of a solid sphere because this is solid. And so for this one right here, what we know is we're looking for minimum force. Well, since this is rotating, really what we need to find is we need to find the torque. Because if we can find the torque, then we can use the torque equation the first torque equation to figure out the force. So to find the torque, we really have, as we said, two different equations. We have tau is equal to FR sine of theta, and we have that tau is equal to I alpha. And so in this case, we know 2 radians per second squared is the angular acceleration. And so that's right here. And so really, let's go ahead and start using our tau equals I alpha equation first. So tau equals I alpha. Let's plug in what we know. So for tau, we don't know that. I is the moment of inertia. We can figure that out because we have our equation right here. So I is equal to 2/5 times the mass of the object, which is 200 kilograms. And that's in the right unit. And then r squared is 80 centimeters, which would need to be 0.8 meters squared right there. And so when we go ahead and do that, see 2/5 times 200 times 0.8 squared comes out with a value of I is equal to 51.2 kilogram meters squared. Okay, so we have our value of I for this, so we'll go ahead and put that in. So 51.2 kilogram meters squared right here times alpha. Alpha is the angular acceleration, which it said is 2 radians per second squared. That is the right unit. We do want it in radians per second squared on that. And so just tau equals I times alpha. So we solve for the torque, tau. And so multiply 51.2 times 2 is just 102.4 is going to be Newton meters, unit of torque, is going to be our torque. Now, question was what minimum force is required. So we have to go from torque to force, and that's where our first equation is going to come in right here. And so torque is equal to force times the radius times the sine of the angle between the force and the radius. And so that we would say tau, which is 102.4, is equal to the force, which is what we're looking for, F, times the radius. Well, what's the radius here? Well, this solid sphere, is on the ground like a large rock or something. We know that the radius that's right here is 0.8. If we want to actually roll this thing, if we want to get it rotating, we'd push up at the top part because, we're looking for the minimum force required. So we don't want to roll it from inside. That really wouldn't be possible. We're going to push on the outside of the rock, and we want to make sure that basically that direction of the force is perpendicular to the radius so we can maximize the torque we get for minimum force. So that'll be our setup right here. And so that's our force. Perpendicular radius along the surface here, and so then because it's the surface, the radius is going to be 0.8, okay, meters, and then sine theta. So theta in this case we said is a right angle, so it's sine of 90 right there. Well, sine of 90 just turns into 1, and then so 102.4 equals F times 0.8. So 102.4. Oops, that's not right. 102.4 would equal to 0.8 F. Divide both sides by 8/10. And so we have to apply a force here of 128 newtons whenever you take 102.4 divided by 0.8. Sig fig wise, since we have 2, it's just 1 sig fig, 80 just 1 sig fig, 200 1 sig fig, everything's 1 sig fig. We just round this to one significant figure, and so we need to apply a force of 100 newtons to the sphere to get it to rotate with an angular acceleration of 2 radians per second with that applied torque. Okay, so let's look at another torque problem. So a 200 Newton force is applied to one end of a barbell, which the force is perpendicular to the 1.6 meter bar, causing the barbell to rotate about the center of the bar. If the barbell has 20 kilogram weights on each end and the bar is massless, what is the linear speed of the weights after 30 seconds? So in this situation, we have our barbell. Here are the two ends on said barbell. Each one is 20 kilograms. We are rotating this barbell across the center of the axis right here. We know that it's a 1.6 meter bar, which means that the distance to the centers in both these is going to be 0.8 meters for both objects. Okay, we have that right there. That's our setup here. We're going to apply this torque. It's a 200 Newton force, okay. So we have a 200 Newton force, and so that means, at that distance right there. Whoops, I don't know what I just did here. Let's see here. I'm going to escape that if I can. No. I don't know what I just did. Let's see if I can get this fixed. All right, let's go back here. All right, so there we are. There we are. All right, so we're going to apply, as we said, our force down right here, and that's 200 newtons to make this thing start rotating. It'll be at that distance of 0.8 from the axis of rotation. All right, so we're looking at how fast the weights are going, linear speed after 30 seconds. So, well, we know the force, we know the location of the force here. Really, if we're looking for that, we're going to need to use a torque so that we can find the angular acceleration. So first, in terms of setting up our torque, we'd say, okay, so tau is equal to FR sine of theta right here, and so then tau is going to be equal to the force, which is 200 newtons, times the radius, which is going to be 8/10 of a meter right here, times the sine of theta. It's perpendicular. The angle that we have right there is perpendicular between the axis of rotation and the applied force. And so sine of 90. And so solving that out, 200 times 0.8 times 1, because sine of 90 is 1, turns out to be 160 newton meters. Okay, so we have our value for the torque right here. We can find the angular acceleration because we know that tau is equal to I alpha. So we know tau is 160 newton meters. Moment of inertia. So in this case is that since the two objects are fairly far, just very decent distance away from the central axis, we can treat these as point masses. And so to solve then for our moment of inertia, we'd say moment of inertia, since we have two objects, it would be the mass of the first times the radius of the first squared plus the mass of the second times the radius of the second squared, right up there. And so then we can go ahead and put these in. So the mass of the first object is 20 kilograms, that should be the right unit here, times the radius is 0.8 meters squared, plus the other object, which has a mass of 20 kilograms, times a radius of 0.8 squared. And so whenever we do this, solving this out, 20 times 0.8 squared comes out right at the 25.6 kilogram meters squared. All right, so we can go ahead and put that in, and so 25.6 is going to be our I, and then times alpha, which is what we're looking for here. All right, so in doing that, let's see, we're going to divide both sides by 25.6. Should give us our angular acceleration, and so in doing that gives us an angular acceleration of 6.25 radians per second squared. So 6.25 radians per second squared. All right, well that gets us the angular acceleration. And it wants to know what the linear speed of the weights is after 30 seconds. And so, to find linear speed, we know that there's a relationship between the two, that the linear speed of an object is equal to the linear velocity of an object is equal to the angular velocity times the radius. And so really we need to find is angular velocity right here. Now the relationship between our alpha, our angular acceleration, angular velocity, is that the angular acceleration is equal to the final angular velocity minus the original angular velocity over time, omega f minus omega o over t. Remember, that's our version of our definition of acceleration equation. And so let's see what we know here. So alpha is 6.25, so 6.25 radians per second squared equals omega f, the final angular velocity, which is what we're looking for. I'll just leave it as omega f here, minus the original angular velocity. Well, presumably this barbell was not moving, not rotating to start with. We really didn't say it, but that's what I meant when I set up the problem. So over the time, and the time here is 30 seconds, and 30 is the right unit for this because we have 6.25 radians per second squared, so 30 seconds should be what we have down here. Multiply both sides by 30, and so that gives us a final angular speed, final angular velocity of 187.5 radians per second. And so now we just need to find the velocity, and so that's where we're going to go back to this guy right here, the linear velocity. And so we would say that the linear velocity is going to be equal to the angular velocity, which is 187.5 radians per second, times the radius, which was 0.8 meters. Okay, and so 187.5 times 0.8 ends up being 150 meters per second. significant figure-wise. 200 has 1 sig fig, 1.6 is 2, 20 has 1. We're all multiplying here, really, except for our moment of inertia right up here. And so this should end up being 1 sig fig. Sorry about that, 1 sig fig. And so our final velocity would be 200 meters per second, which is a good speed on these guys, and that's the reason why is we're applying a decent force for a long time. Application of a 200 Newton force for 30 seconds is a long time to apply a force, and so as a result, that's how fast the object would be spinning. The barbell ends would be spinning after this 30 seconds.